Okay, everybody. Welcome back to System Software. Let's get started. So today was the due date for Project 1. How did it go? Went really well? Good? One thumbs up out of everyone? Okay, a few. Okay, so hopefully now, if you were uncomfortable with recursion before, hopefully you're a little more comfortable with it, or you just did postfix to infix to postfix and sort of got around having to learn recursion. But in the future, the more we extend the language, the more you're going to have to do recursion. And my opinion is that it's actually easier to solve these algorithms with recursion than it is to make up a new algorithm, like with infix to postfix. But you'll have plenty of opportunities. I'll try to cover more recursion as we go along, because I think it's a really valuable tool to have in your toolbox as a programmer. It's a really easy way to decompose problems. Also, when you go for coding interviews, they may ask you some recursive algorithms to implement them. Anyway, questions about Project 1 or questions about parsing in general, top-down parsing, bottom-up parsing? Everybody's all good? Questions about code generation for the expressions? Yeah.
When it comes to generating the embedded code, would you recommend, is there a specific method to that you would recommend over others? For example, one way, of course, is creating just one giant string that you can add the characters onto, as you parse through the input. Another would be just embedded as you go. What would you say?
Right. So where do you store the emitted code? Is that what you're asking? Yeah. I mean, well, for this project, just had you just print it out to standard out, since that's why I thought that would make it a little easier if you just have to.
From a higher level, say we were actually making a full out compiler, like the GCC.
Right. Well, they actually have you guys are using an intermediate representation, LLVM-IR, and most modern compilers do that as well. But internally, they'll have data structures that represent the IR in memory, so that you can just store it in memory. That's even faster than doing file I/O. So when you see Clang, the toolchain, they're not going to write it out to text and then re-parse that text. They're just going to store it in a data structure in memory, and then do all the rest of the compiler workflow from there, like all the optimizations. Then they're going to work on generating machine code. So it'll be left in memory until it absolutely needs to go out into text or go out. I mean, it'll never reach text. It'll go out into binary ultimately. But LLVM is a really nice toolkit. They've got actually binary formats for LLVM-IR as well, so that if you, for whatever reason, don't want to store it in memory, you can actually write it out as a binary file as well. I think they're LLI files, maybe. Anyway, they have a binary format as well. But the emitted code will be in memory for further optimization and code generation. Yeah, that's a good question. Okay, any other questions? Anything else? Okay, so let's move on to the next part. Just as a reminder, if you didn't turn Project 1 in today, it's only 1 point off for the next 2 weeks, then 2 points off after that. But today we're starting Project 2, which is the third project, base zero indexing. And so we're going to take our language. So our language, if you remember, our language can print arithmetic operations out, and that was Project 0. And in Project 1, we could print arbitrary arithmetic operations, but everything was still constant values. You can't really do full computation with that. So the next thing we're going to add to our language is support for variables. And I'm sure all of you have taken CS1 and 2, have done programming, so I'm sure you're all familiar with using these variables. So for this project, we're going to learn how we actually define the language for variables and how we can actually write a compiler that can implement variables. So in machine code, if you remember from computer architecture, there's no real notion of variables. You can't create a symbolic name. In assembly, you kind of can. The assembler can kind of do it. But at the machine level, everything is just memory addresses. There are no symbolic names for the data that you want to work with. And so what our compiler is going to do is it's going to take this world of symbolic names and it's going to map them into memory locations. So first, let's look at what the, let's just look at variables sort of overall for a second. I think these are inspired by algebra. This is just my guess. I didn't actually look this up, but it seems pretty clear that this is sort of inspired by algebra, where symbols are used as placeholders for numbers, for actual values. So for instance, y equals x plus 1. In algebra, this would be an equation that says that y is always equal to x plus 1, and then you can do all kinds of solving and substitution to do this. But it's more of an analogy in programming languages, at least in imperative programming languages like C or Java. In these languages, the equal symbol, even though it looks very much like equality, is not quite equality in imperative languages. It actually means assignment. And so assignment is kind of a different notion than equality. For instance, if we have a program that says x equals 1, and then the next line it says x equals 2, well, in math, that would be wouldn't really make a lot of sense, right? You're trying to say that x is equal to two different values at the same time. 1 does not equal 2, at least in our axioms of arithmetic. So it's not quite equality, it's assignment, because variables in programming languages hold a value rather than making statements about the equality of these symbols. They're storage, they're holding a value, and these values can change. You can reassign the variable. In C, at least, you can reassign the variable. And it's worth noting that if you take programming languages, I don't know if you've taken this yet, I actually subbed today for Dr. Levins, but if you take that class, you'll learn more about functional programming. And in functional programming languages, variables are immutable. Variables can only be assigned once. So it's sort of a little bit closer to math, but still programming. But in simple C, our programming language, our variables are mutable. They can be assigned and reassigned. And so for project 2, the grammar adds a couple of different new language constructs and new language constructs and new grammar. So we can, whoops. What is this? Okay. So we can, of course, declare variables like we do in C, and it has a very similar syntax to C. We can assign variables like so. We just say x followed by the equal sign, followed by some math expression. And we can use these variables in other expressions. So in the print statement, we can use x. So pretty straightforward, right? I think this should hopefully be all pretty clear to you if you're using C. So here's a complete example. We declare a variable x. We assign that variable to some value, and we print out that value, print out an expression that uses that variable. Pretty straightforward, right? Any questions on this? Any questions just on the semantics of simple C? Yeah.
Are we going to be able to declare and initialize a variable on the same line?
No. You're free to do that. If you want to add that to your language, go for it. It's just
but
more.
But we're not going to have to write.
Right. You don't have to. You don't have to. So you can think of that as like syntactic sugar for both declaring and assigning a variable. But I wanted to make the grammar like as simple as I could. So I tried to avoid a lot of syntactic sugar. Yeah.
Just like when you are setting up this variable, you wouldn't just call expression in order to set it. It would be like a temp variable at the end of it if you did it that way.
Yeah, I mean, the way all of this will work is through these temporary variables.
Okay.
But there's more you have to do with variables, and we'll get into how variables are implemented under the hood with the IR. But yeah, you could certainly, and actually, if you want to make up your own bonus project, feel free to extend the language. Show me. You can get points for that. We can, if you want to do an extra project. But I tried to make the grammar really simple. So, for instance, well, yeah, we might as well look at the grammar for this. And I should have highlighted. So I'll highlight what the differences are between project 1 and project 0. So I try to put in a little blurb about what actually has changed between the two languages after each grammar. But the only thing, okay, well, how about you guys? What spot the differences? What has been added to this grammar from project 1, since you're all expert on grammar, the first grammar? Yeah, either. Yeah, go ahead.
Ladies first.
Okay.
Int identifier, the declaration.
Right. So we've got a declaration non-terminal. We never saw that before. So we've got declaration. So this covers exactly that declaration syntax. We have an int keyword followed by an identifier terminal followed by the semicolon. Pretty simple, right? Just 3 terminals in a row. What else? What else is different?
There's an identifier and expression now.
There's an identifier and expression. Good. So one of the So in the grammar that's rewritten for operator precedence, which we've got expression, term, and factor. Which of those 3 non-terminals will identifier fall into? Maybe there's a little trick question. Which one of those do you think?
Either factor or none of them.
Either factor or none of them. Any other takers? Who says none of them? Who says in factor? Is there something else? Yeah, you had another opinion? Oh, okay. Yeah, it would be a factor. It's just another factor. So the same level of factor. Okay, so that's another difference. What else? Yeah.
Program application production.
Ah, good. Program's production is now different. So how is it different?
It used to be just statement star.
Right, it used to be just statement star. Now we've got declarations followed by statements. So what does this mean? What kind of what does the program have to look like according to this program production? Yeah.
0 more declarations followed by 0 more.
Right. 0 more declarations followed by 0 more statements. So can I have declaration, statement, declaration? No, right? All the declarations have to be at the top. This is also for simplicity. This should make it a little easier to write this compiler. So I think even classic C, like one of the earlier versions of C, actually enforced this rule as well, where all declarations had to be at the top. You couldn't say like for int I. You couldn't even do that in early versions of C. So it just makes writing the compiler easier. Any other differences? This is like game of spot the differences. Yeah.
So under statement, did anybody mention that identifier assigned expression?
No, nobody's mentioned this. So we've got identifier, assign, expression, semi. So in case you don't remember the lexical specification, the assign terminal is just an equals symbol. So remember, all the capital stuff is terminals. So yeah, so this is the syntax for doing an assignment, variable assignment. So like x equals 10 plus 2 or whatever the expression is. And notice here that in project 1, the code generator was written so that when you call the expression non-terminal, what does it return when you call the expression non-terminal? For those of you who wrote it with the recursive technique. Yeah, if you call the expression non-terminal in the recursive version of the code generator, what does it return?
It returns expression.
It returns a variable. Yeah, it returns the variable or value of the expression. So to kind of give a little foreshadowing to the implementation of this, to implement this statement, we just simply call the expression function. We call the expression parser. It's like a parser for that part of the grammar. And when we do this variable, when we actually implement this variable assignment, we don't have to care anymore about how expressions are implemented. We just simply call the expression function. As long as it's correctly written, it'll give us back a temporary variable or a value. And we just use that to implement our variable storage, to variable assignment. Anything else? Any other differences? Yeah. Oh yeah, read, good. Read identifier, semi. So this is just the read keyword followed by an identifier followed by semicolon. So what do you think this is going to do? Take X, yeah. I'll go over this in the slides, but yeah, we're going to actually do some input to these programs. This is how we can read values in from the user. Okay, questions so far on just the kind of new syntax of this? So I think that's pretty much good for a demo. I think we all pretty much understand what this looks like. All right, so for reading from input, we're going to also be able to use these variables to read from input, because if we just have constants in our program, there's no way to specify any kind of variation. We always compute the same value every time we run the program. But if we want the program to be able to compute, say, the force of gravity between two bodies, and we want to have variables for those for those for the distance and for the weights of these things, then we need variables to do this. This is kind of the inspiration from algebra, where you can make a more general formula that use symbols as placeholders for values in the future. But the way we actually get those different values in order to execute the program is we need to read them in from somewhere. We need to get some input for this. So this new statement in simple C that I've given you just uses the read keyword, just like print prints out standard out, read reads it from standard in. So some of you noticed that there's a new template.ll. So I extended this to have some functionality to read in an integer. And the way it works is it prompts the user, reads the string from standard input, converts it to an integer, and then just passes it back to you. So just like print, you can just pass in your value you want to print. With read, you just call read and save it into a temporary variable. So I think this is kind of a good point to be a little clearer about what I mean when I say standard in and standard out and standard error. This is a Unix or a POSIX thing. This is like a standard for operating systems. Every process that you create by default has these 3 files already opened for you and ready to read and write to. So just as a little refresher from like lecture 2 or something, in operating systems, a process is just a program that's running. The program you can think of as the binary machine code. And then your operating system loader puts it into memory. The kernel jumps to that point in memory and starts running it. At that point, it's a process. It's a running program. But by convention, in Unix systems, and I think probably Windows and any POSIX compliant systems, POSIX is a standard for Unix-like operating systems. The operating system sets up the process to have these 3 files. And in Unix, the files are just numbered in a table starting from 0. So if you open a bunch of files, they each get a new file descriptor, which is really just a number in a table. So the first 3 elements of this table, 0, 1, and 2, are the standard input, standard output, and standard error. So file descriptor 0 is standard in, file descriptor 1 is standard out, file descriptor 2, standard error. So you're just given these 3 files. What's really useful about this is that what these files actually are depend on how you run the program. Depends on the parent process that actually created your process. So when you're running stuff from the command line, when you're in Bash and you run a new program, by default, Bash will set up all 3 of these to be your terminal file. So in Unix, all I/O, at least traditionally, all I/O is done through files. So even though you want to write to, say, a hard disk, or you want to write to the network, there's a special file in your Unix operating system in that /dev folder, if you've ever looked at that. There's a special file that you can just read and write to like any other file on the file system to do I/O. And so when you have this terminal window open, there's a special file that when you read and write to that file, reads from and prints to your console window. So when you type in the keyboard, it can be read from a special file. And so what's so powerful about the Unix command line is that we can manipulate these 3 files. We can manipulate what the standard in, standard out, and standard error are. This is called redirection, changing what these files are from the default. So for those who are wondering why there's that little angle bracket when I asked you to run simple C and save the output to a file, why that happens, it's because the Bash shell, you're telling the Bash shell to, instead of writing out the output to the terminal file, write out the output to the file that you give on the command line. So in Bash, all of these can be changed with some special syntax. So if we want to redirect the output of a command, then we use this syntax. We run the name of the program that we want to run. We give this little angle bracket, a greater than sign, if you will, and then the name of the file, the path to the file that we want to save the standard out to. If we want to redirect the input to a file, so sort is a program that will take a text file in and sort it by lines, sort the lines of it. We can do the opposite direction. We can do a less than sign. So it's kind of like pointing to the program, right? It's like this, kind of looks like this file list is pointing to our program. That's one way to remember it, perhaps. And this will, instead of reading from the terminal, where you have to actually type something, this will take the contents of a file and use that as the input for our sort function. So to look at a little example of this, here's my home directory. So if I type ls, that gives me the listing of the files. But instead of having it print to the terminal window, the console, which is a special file in is it TTY? Where is it? So it's the special file here in dev, I think. Yeah, I think it's dev 0. So there's a special file that's the terminal here. So I actually just I think I can write to it. Maybe not. Oh yeah, there we go. So if I write to this file, PTS1, that's my terminal window. That's the file that represents my terminal window. So if I write stuff to that file, then you see it appears on my terminal window, because my terminal window is just a special file that when you write to that file, it prints out to the terminal window. When I type text into my terminal window, that comes out of that can be read from this file, dev pts1. But anyway, take operating systems. Hopefully you'll learn more about that. There. So if I, instead of printing to the terminal file, I can save this to a new text file. So you see, you don't see anything come out in my terminal window because all of this has been written to my file. So cat is a program that just prints out a file, reads the file in and prints it out to standard out. So there you can see my file list here. Now sort is a program that just reads from standard input and sorts all the inputs line by line. Now right now, if I run sort, it looks like the program's hanging, but really it's just waiting for input from standard in. Standard in now happens to be my terminal window. So if I write a bunch of things here, Control D means end of file. It's a little hard to see, but it immediately printed out the sorted version of what I inputted. Make sense? And I can even do both, redirect in. So here's redirecting, here's sorting the file list that I have. Actually, it was already sorted, so it's kind of pointless, but redirecting the file list, and I can save it, I can redirect it out to another file. So I can do both at the same time. I can change the input and I can change the output, and they can be different things. So now I've got this sorted version of my file list. Questions on this so far? Questions on this? A little command line foo here, command line magic. So probably one of the most powerful things in the Unix command line is I can chain multiple programs together. So rather than just redirecting to files, I can redirect to other programs. And through this, I can build up basically a new program. I can chain together a bunch of little programs and build that up to be basically like construct on the fly a large operation. And this is done with the pipe command. So if I do pipe sort, this is exactly equivalent to redirecting the output of the ls command out and then redirecting the input of the sort command. That is exactly the same, or at least equivalent to doing this, where I say ls pipe sort. It takes the output of ls and it turns it into the input of sort. So you can do some pretty fancy things with this. Find will give you every file in that directory. So if I want to look at every file in my file system, I can say find /. And I can use this to actually use regular expressions to search for particular files. So if I want to look for particular files that say start with /, let's see. If I want to look for files that start with, files that have the word hash in it, then I can take the output of find /, which is every file, lists every file, and then I can pipe it to a program that will apply a regular expression to that list. So you can see that the output of this, so it went by pretty fast, you can see it has only the files that have the word hash in it. So I've just constructed like a file system search in like 2 commands on the command line with a single command line. This is a pretty powerful thing. I actually use this pretty regularly, these kind of things, when I'm doing coding and research. So you can see now I've got a list of only things with hash in it. Now notice here that I got a bunch of these permission denied errors. These are actually errors from the find command. So even if I didn't pipe it, I would get these errors from find. And the reason that they're not being sent to grep is that there is a third file descriptor, the standard error file descriptor. And this is just a convention. This is really just a convention in the Unix kernel or the Unix style of operating system. So every program is given not one output, but two outputs. One is the standard error, one is the standard out, one is the standard error. So why do this? There's really no technical reason for this. This is really more of a convention for users. So standard out is just by convention where you put the normal output, the output when nothing goes wrong. And standard error is for like diagnostics or when there's an error or when there's something goes wrong. So the find command, if I redirect its output to nothing. So this is a little trick you can do. If you don't want to see any output, you can redirect it to /dev/null, which just destroys anything you have. It doesn't actually save any data. Then you can see all of the error messages that I get from find. You with me so far on this? Does this make sense so far?
Yeah.
So there's two types of output. There's two output files for every program. One is standard error, one is standard out. So if I want to save standard error, so here is the standard out with my greater than sign. I can save the standard error using 2 followed by the greater than sign. Syntax is a little esoteric. This is old school bash syntax from probably decades ago. But this is how we can save these 2 different outputs from our program. Okay, so it ran and it finished surprisingly fast. So if I take a look at standard out, I get all of my files printed out by find. And if I look at standard error, I get all of the error messages that find printed out, because these are like really 2 separate files. Yeah?
What is that
Less command? Which one? When I do this? Oh, I'm sorry. Less. This is a little pun from, this is a nerd pun, I guess, nerd humor. There used to be a program called more. Like cat will just print out the whole file to your terminal. More will print it out with this handy little paging functionality. But with more, you can't go back in the file. You can only go one direction through the file. So less, these are computer programmers, okay? Leave comedy to the professionals. Less will give you a more rich version of more. So you can go up and down in the file. You can use page up and page down. So I'm going to the top of the file. I can go to the bottom of the file. You can jump around. It has its own syntax, or it has its own commands. You can type H for help, but I only use a few of them. But you can, it's just a way to like view a file really quickly on the command line. So more command line foo. Okay, questions on this so far? Pretty straightforward, right? You're all going to be command line ninjas in no time. All right, so some other tricks. I sort of went through some of these already. You can redirect to /dev/null if you don't care about the output. So in this find command, if I didn't want to have to look at all that error output, I could have redirected the standard error to /dev/null, and then piped the standard out to grep in order to search for all the files that have hash in it. So now when I run this command, I will just get a list of things that have the word hash in it without any of those pesky error messages. And I can continue with this. I can sort that output now if I want to have a sorted list of all the ones with hash in it. I can find all the things that are not duplicates. Of course, there won't be in the file system with unique. But anyway, you can chain these things together and do really powerful things. You can even search inside of these files. So this is just a little taste, but I won't go in it. So this is all the files that have the word hash in the file. But anyway, so if you want to pipe both standard error and standard out, this one I learned this year actually. You can do pipe and ampersand. They're all kind of esoteric. You get used to it when you do it over and over. And this is just an example of doing all 3. So why is this useful? So in our upcoming compiler, your programs will have standard in, because we now have reading variables. They'll have standard out, of course. This is the programs that you compile, the simple C programs. And your compiler will now have to report errors. So now that we have variables and we have to declare variables, we also have undeclared variable errors. That's the first thing we have. So your compiler is going to have to report undeclared variable errors, and the graders will expect that to be in the standard out of your compiler. And it's pretty straightforward to do. You just use fprintf and the standard error keyword. So when you include standard io.h for your printf and fprintf, there are 3 variables given to you: standard in, standard error, and standard out. And those are just files, just like when you do fopen and you get a file descriptor. These are just special files that represent those 3 standard IO that you get for every process. So all you have to do when you want to print out an error is just say fprintf, and then the file is standard error. And that's it. Did you guys learn this in like CS1 or CS2? Nothing about this? Okay. Sort of?
Yeah.
This is maybe like OS related. So anyway, we'll talk about code generation more, and feel free to ask on Piazza and everything. Okay, so I think we already went through a demo of redirection and piping. So questions on this at all? Questions on this? Yeah.
So in project 2, we're going to have to have that error checking for not properly declaring it into
Yep.
variables.
Yep. Yeah. Yeah.
So is it going to be like, say, you just say X, or is it going to be something like?
Oh, okay. That's a good question. That's a good question. So to make this concrete, I've given some test cases to see what the error message is supposed to look like. So these are a couple of examples. So here, example 3 declares X, but then it uses Y when assigning X. And I think I say this in the project description as well. If the program has an error, the output is considered undefined. So we won't even check the output of your compiler. It can be incomplete, it can be incorrect. It's undefined behavior, yeah.
So when we're reading, I just want to compiler, going to the bottom, like
Yeah.
these variables, we'll have to store these queries, variables, and keep track of which ones are.
That's exactly right. We're going to have to keep track of these variables as we process the file. That's exactly right, and that's what we'll see today and over the next couple lectures of how we do that, how the compiler tracks these variables, and what information we need about these variables more than just the symbol itself. So yes, to look for undefined or undeclared variables, yeah, we need to track the names of the variables, but we need a little bit more for the compiler. Yeah.
And we're going to want to differentiate the exact error line that you're giving in the example.
The exact error message? Yeah. We're going to match the error message. That just makes it way easier to grade. So I've made a new type of file called ground truth error, or ground truther, unfortunately, is what it looks like as well. So this is what it will look like. And it just has a pattern here. So if you notice an undeclared use of a variable, you can just print out this string and have a %s for the name of the variable that is undefined. So this is giving a little bit of more feedback to the user about what is undefined. So much like when you use GCC, you give some feedback. Sometimes it's convoluted, but you get some feedback about what the compilation error was. So notice I don't even provide a ground truth for example 3 because the program could not be compiled. It couldn't be output. And for the .ll file that it's output, for printing out, we won't even check that because if we see an error, we assume that the output of the compiler is already undefined behavior. Yeah.
Are we going to want to have it like where in the code?
If you want to do that, yeah, please do. You can use that as a bonus project. If you want to have better so error messaging itself is like a big engineering problem, especially in compilers, really in any software, having good error feedback. It's a user experience issue to have good user feedback. And particularly for compilers, when you have very intricate code, having very detailed feedback about where errors is important. So Clang went a long way in improving error message feedback. So you'll often see like line number and column number, and because you're reading one character at a time, how would you track the line and column number? How would you track the line and column number?
Every time it sees a backslash n
Yeah.
and row +1 and
Exactly right. Yeah.
that you're reading afterwards, it's char +1.
Yeah. So you know exactly where the new line characters are because you're reading character by character. And when you see a new line character, you know that that's a new line. So you just keep track of how many lines there have been and how many characters they've been in each line, and there's your line and column number. So yeah, as a bonus project, feel free to do that. Let me know so I can grade it separately. But yeah, you can totally do that. Get some bonus points. But no, we won't expect you to have to do that. Whatever the ground truth, as long as it's correct, whatever the ground truth is, that's what your program should output. Unless there's a bug, in the examples. But this should give you what will actually match. And the grader scripts will be updated to check this as well. So when you run the grader scripts, you can check for yourself. Okay, other questions on this? Other questions? Okay, any other questions on redirection and piping? Okay, it's a useful thing. I mean, I hope all of you will, learn more about the command line after this and become command line experts. Okay, also so I realize that, using these templates is a little bit of a pain. There's special characters when you do printf, like the %sign, and those are all over the place in the template. So I've created a header file which has the template broken up for you into 2 macros, which are just big long strings, and you can just use that. So you don't have to worry about all this, struggling. Yeah. It took me a little bit to figure out all the things that I needed to escape, but basically it's only 3 things. You just need to escape the %sign, quotes, and backslashes. You need to escape those, but %signs are escaped by doing 2 %signs instead of backslash %sign. But anyway, you don't have to worry about it anymore. I've already done this for you, and you can find this inside of the project folder. Well, let me show it to you on GitHub. So you can find this inside of the projects folder under template.h. So I've just made 2 macros, and I've done all the formatting to turn it into one giant string. So interestingly, in C, you can actually have multiple quote delimited strings next to each other, and the C compiler will just turn that into one big string for you. This little backslash at the end of a line is, believe it or not, escaping the new line character itself. So if you want to, it's called a line continuation. So if you want to write one big long line, but you want it to be broken up on separate lines in your source file, you put a backslash as the very last character on the line, and it effectively escapes the invisible new line character. So this is equivalent to just having all of these lines on one big long line to the C compiler. So you've got one macro called prologue, and that'll give you everything you need to put before your generated code. And you can see now it has our new read integer function in here. And we have the epilogue, which is everything that needs to go afterwards. Yeah. Good question. How do you print these out? So I've given you also a little example of using this in template usage.c. So prologue is just a macro that expands to this giant string, and you just use printf epilogue, and it does all the nice new lines for you, so it'll be all nicely formatted. And same with epilogue. So in between, that's where you do all your code generation. So in your main, beginning of your main, you do prologue, end of your main, you do epilogue, and then you do all your code gen in between. So I know some of you were struggling with this, and maybe you probably would have liked this before, but I figured this would be easier with the new template. So just to show this working. Whoops, not that one. So here's my example. If I compile this and run it, I get a giant.
Yeah,
I get a giant LLVM file. But you see, it's all nicely formatted. It's got all the spacing and the new lines all in the right places. And this is what I generated, although I did the wrong indenting. So actually, here's an example of using read integer with print integer. So let me just run this. So when I run it and use this new read integer function that I've given you, whoops, that's not running it. Oh, that's the program. Okay, that's the program that generates it. See, I got confused about the compiler stuff. So template usage generates an LLVM program. So here's my LLVM. I saved it to a file called LLVM. Now I got to compile it. Compile the LLVM program. Fortunately, it compiled. Now, when I run it, here's what happens when you use the read integer. I actually prompt the user. Let me actually check if make sure this is not standard. Okay, good. So I actually prompt the user in standard error so that it won't interfere with the output. And I prompt the user because last semester when it was hanging on blocking waiting for standard in, some students believed that their program was hanging, but actually it was just waiting for input. So if you see that, please enter integer and nothing's after it, then you can be pretty sure that it's just waiting for input. So I can, put in some random number, and I stored that in standard out. So that's what I get in standard out. Let me run that again without having the redirection. Whoops, that's not a number. So I won't give you cases where the input won't be formatted properly.
Yeah.
It does, because I use A to I. I use A to I. So use A to I function just for this. So that's all it does. That's all read integer does. All right, questions on this? Questions on the new template? Oh yeah, and to use it, so this is when you use double quotes for include, that looks at your so in this case, it's going to look in the current directory where it's being compiled. You can actually add new paths to this. There's a whole way to add search paths to this. So in this usage, it's assuming that template.h is in the same directory as your source file. So just like the make file, just copy it in. More practice, on the command line doing copying. Good to know your file system on the command line. Yeah.
Okay, so we could just copy template.h into our source file.
Yep.
Stuff, and then we just would put in printf and then run everything that we need to run for all the stuff in main and then the epilogue part.
Yep.
Right?
Yeah.
Okay.
That's right. That's all you got to do. So all your code is just going to go right here in the middle, and just include this. Copy template.h, include it, and you should be good to go. Yeah. Yes. It's part of your source code now. So to make sure it's under version control, make sure it's part of your distribution, part of your source code. So I know that the GitHub stuff is a little tedious, but when you go out there and you become big software engineers in Google and Facebook and all these big companies, you're going to be using version control. And version control means it tracks every addition and deletion to that code base. And that's really right now it's like the minimum standard for doing reliable software development. The old days of having it on some network file system or on your local drive and, I don't know, emailing source files around, that's over, hopefully, in most places. Version control is, the minimum you need for building reliable software. Necessary, but not sufficient. Okay, any other questions on this? Okay, so that's the new template. Let's see what's next. Okay, so let's actually talk about how these variables get. Oh, I'm sorry. Go ahead.
So I have a question about the new tests.
The new tests.
Will you just be typing in the standard input?
Yes.
To replace the script for that, or?
Exactly right. Yeah, the scripts. So the scripts will. I don't think they've been updated yet, but no, that's a good question. The scripts. Let's see. So, for instance, in example 2 here. Where is this? So in example 2, oh, this reads as well. So this will actually have standard out. But okay. So basically, the logic of the greater scripts that I'm expecting is it will look at the stem of the file and it'll see, what files are there. Is there an input file? Is there an output file? Is there an error output file? And if there's an input file, it'll use that as the input. So you don't have to make your own. You don't have to pass in your own. We provide you the input for every program. And so we're basically just gonna, once we compile your program and turn it into an LVM program, we'll just run, we'll run this. Actually, I wrote a little script that pretends to be a working program called, what did I call it? Phony run. Yeah, so it'll be run like this. So if I've got my project 2, or example 2, the input will be redirected in. The output will be saved to example 2.out. And the standard error, if there's a ground truth error, that will be saved to standard out. Or standard error, rather. Sorry, that'll be saved to a file called standard error. In this case, there is no ground truth, so we won't bother saving the output of it. So if we run that, then the output of your program will be stored here in example 2.out. Okay, usage from your run. Oh yeah, let's call it this. What did I call it? Oh yeah, like this. Okay, well that didn't work. But anyway, so I thought I set this up to. Why does this not work? Oh right, I didn't give the full path to it. Okay, so yeah, so it'll save it to out, and then it'll just do a diff between. So this is also a very handy command line tool. It'll just do a diff between your output and the ground truth output. So if there are no differences, then diff won't output anything. It'll have a return code of 0, which we can see like this. If there were differences, like if I compared, let's see. So if there were differences, it'll give you this little, I think you see that when you run the greater script, you'll see this little format where it shows you the differences between the two files. This arrow means the left file, this arrow means the right file. But yeah, anyway, we'll take the whatever input file we have and we'll pass it to your compiled program and check to see if the output matches. And then, there'll be some logic, if there's a type error and they're supposed to have a type error, we'll save your error output and make sure it matches the ground truth error. Other questions? Other questions on this? So hopefully the scripts will be updated soon, so you can test them out. But in the meantime, now you know how to do this file redirection. So it's a little tedious on the command line. So just in case, for those of you who don't know yet, I basically hit the tab key probably like 100,000 times a day. So tab will automatically complete complete the file for you. So if I so right now I'm just hitting tab repeatedly. If I keep hitting tab, it will just start finishing the command line for me. So I hit 2, it'll just keep finishing the command line for me until there's not, until it finds a prefix that's not unique and finds that there are many possible suffixes. So if I then say example 2, it'll complete the period for me and tell me all of the other extensions that I can put in. So if I just hit G and then I hit tab, it'll just automatically complete the file for me. This is what makes using the command line tolerable. Without that, it would be rough to be able to tuck all these in. So, keep in your mind your file system, where you are in the file system. If you need to know where you are in the file system, type print working directory, PWD. That'll tell you where you are. Just keep that in mind, and keep in mind where the syllabus tests are, where the greater scripts are. And then, you can use the command line like a pro. All right. Okay, so let's move on to how variables are actually implemented in the machine. So as I mentioned, the machine doesn't have any notion of like symbols, doesn't have any notions of text, just has memory addresses. And so for simple C and for most imperative languages, variables correspond to locations in memory. But to see how the program manages this memory, like where this data is actually stored, the operating system and the machine work together to provide you these sections. It sections off the RAM into special purpose locations. So even though conceptually you have this giant list of memory addresses from your RAM DIMMs, the operating system and the compiler organize that memory in a specific way. So at the beginning of this section of memory, so the operating system will give you a section of memory. When you take operating systems, you'll learn about virtual memory. Each program thinks that it has the entire RAM. It's sort of fooled into thinking that through virtual memory. You don't actually touch the physical memory itself. And so every program sees that its program is at the very beginning of the address space, near the zero, near the bottom of the address space. Then there's, global variables are allocated on top of that. So the memory count grows up. So 0 is down here, the low address, the high address is up here. And then on top of all of your assembly segments, so these parts of the memory here are controlled by your object file. So the object file has all sorts of information about where your code is, what your global variables are, what segments of memory you want, so you can actually allocate more than just your global variables. The assembly file gives you control over doing your own kind of custom memory allocation. But then on top of that, you've got your heap and you have your stack. So did you guys learn about this before, heap and stack? Yeah. CS1? You guys all, okay, good. You guys all learned about this. So what is the stack used for?
Your local variable.
Local variables, yeah, it's exactly written here. Yeah, the stack is where local variables for functions go. So every time you call a function, the caller has all of its data stored on the stack, and when you call a new function, a new entry on the stack is created, a new stack frame. And we'll learn about those when we actually implement functions. A new stack frame is created for the new local variables of that new function. So in simple C, we're only going to have stack allocated variables. We're not going to bother with heap allocated variables. What about the heap? What is the heap used for? Stuff outside of functions. Yeah, it's like written there, right? So this is malloc. You usually use malloc to do this. So like technically speaking, you can just, as a programmer, you can write a program that accesses, in C at least, you can access whatever memory you want. You can just make an array and just say, give me address, 0, D8, whatever. Yeah.
Would a global variable be stored in the heap or in the stack?
That's a good question. What do you guys think? Heap? Is it stored in the heap? Is it stored in the stack? Oh, you're all wrong. Yeah. It's stored in the it's stored it's stored ahead of time. The assembler lays that out. It's kind of a trick question. That's where globals are stored. Part of the reason for that is you can actually have globals that are shared between multiple compilation units that get linked together, kind of like functions can be in multiple files. So they have a well-defined location according to the object file. But it's a good question. Where do globals go? Okay, yeah. So heap is usually use malloc or some memory managed allocation to do that. But technically, you can access anywhere. This is really kind of a convention. You as the programmer are free to access whatever memory you're allowed to access in this entire address space. Actually, even in the code space. Although nowadays the code section is write protected at the hardware level. But you can address any of this and read and write it as long as the operating system allows you to read and write it. And actually, when you try to read or write a piece of memory that the operating system doesn't allow you to have access, that's where you get a segmentation fault. Seg fault happens because you're accessing, if you try to access null, that's accessing memory location 0, which the operating system reserves for itself. That's why you get the seg fault. What's that? Yeah, everybody knows seg faults. And actually, one of the reasons why C is a little bad for security is because of this, because the language allows you to access arbitrary memory at any point. In Java, for instance, as long as the type system, in the correct version of the type system, doesn't allow you to access memory outside the bounds of whatever you define in the language. So if you declare a new array, in C, you can happily read outside the bounds of that array, which is the cause of 50% of all security vulnerabilities that are due to software bugs, and growing, because there's a lot of code written in C and there's a lot of memory errors written in C that people haven't even found yet. But in Java, the Java and other memory safe languages, this is not possible without undermining the type system. Okay, so I think this is all review for you. You all know about stacks and heaps. So for this project, or for this version of the project, we don't have functions yet. We only have a single kind of main method that's sort of implicit. We have we have no functions yet. We only have global variables and one function that gets run, one main function that gets run. But even so, all variables are going to be stored onto the stack. So I don't think we have time for this. So the way this is going to work is the compiler is going to create space on the stack for any new variables that get declared. Oh yeah, go ahead.
Why do we need the variables on the stack when the LVMIR allows us to have an arbitrary number of temporary variables?
Oh, that's a good question. Since we have arbitrary temporary variables, why do we even bother using memory at all? Well, so that's kind of a subtle question. If we have a program like this, could we just turn X into, say, a local variable in LLVM and let LLVM take care of it? Yeah, we could do that. You could do that, actually. You could do that. That's a good point.
We found the loophole.
So now we're going to declare X, and then we're just going to return a new variable and then continue on.
Yeah, you actually probably could do that. But I'm trying to think why you shouldn't do that.
Because it checks out.
Yeah, that's not a good. I said so. It's not a good reason. Yeah, go ahead.
I'm guessing here, could it be because you can only have a max of 30 registers, and so if you give LLVM more than 30 temporary variables in a single expression, will it give you an error or something?
That's a good point. I mean, LLVM actually allows unlimited registers, and it does its own. Oh yeah, what does it do when there's more registers? So that's a good question. It must have to do its own register spilling, I guess. Yeah, I actually have to look into that. What it does when you use more.
You know what happens when we try to break the system?
Tempted to just look it up. Let me say, yeah, go ahead.
You use a variable with the new way, if you do it for the dynamic variables in LVM.
Yeah.
They are also not used, right?
That's right. That's true. Yeah. They're not mutable. That's true. But that's okay. You could still use. You could just you could create new variables for them. Let's see. What happens when LVM? I guess it must have to spill the register. Yeah, I guess it must have to spill the register. So the reason I'm having you do stack allocation is because if you weren't using LLVM, you would have this register allocation problem where you wouldn't have a new register for this. But LLVM probably is smart enough to deal with that. But don't do that. Don't cheat. Use the machine way to do it. I think there must also be another reason for this. Oh yeah, of course. So once we get to other functions and you call a new function, what happens to those register values? In LVM, I actually don't know, but when it actually gets compiled to machine code, those variables have to be saved somewhere. What's that? And I don't think LLVM will actually do that for you. I don't think LLVM will save temporary variables for you. I don't think, but I could be wrong. I will look into it though, but I think that's going to be ultimately the reason. That's why we save it onto the stack, because when we call multiple functions, we need a place to store store those values while we go off and do other computation with new registers. And I don't know if LLVM, I don't think LLVM will actually do that for you, but I will check. I will check. But that's a good point. That's a good point. So for this project, yeah, there might be like an easy out to do this. But once you get to functions, then it may not work anymore. And yeah, I'm thinking like at the machine level how this works. Oh, good question. Good question. But I'm going to look into it a little more. Yeah, exactly, to make sure it doesn't work. I think I heard somebody say that. So the way we're going to manage memory here is when we have a new declaration, we'll create a new stack entry for it. May or may not be necessary for this project, but for future projects, I'm pretty sure it will be. And the compiler is going to keep track of this mapping between names and memory locations. In LLVM, this is made a little easier because the memory location is also stored in a local variable. So this is an example of a symbol table. The symbol table records the variable name, its type. So for our purposes, we only have int for this class, and the address in the machine of that variable that the machine has allocated that variable. So when the variable, when you want to assign the variable, the compiler will look up the symbol table, find the address that we're using to store the value of that variable, and will create what did I say? If it wants to assign the variable, it'll create a store instruction that will take whatever thing you're trying to store and put it in that memory location. If we're trying to read this variable, read the value of it, then it'll generate a load and use this symbol table, the address that we allocated in the symbol table when we declared the variable. So we'll talk a little bit more about that and go through code generation. In LLVM-IR, to manage stack variables, there are a couple instructions that you can use. The first one is allocate or alloca, and this will create a stack entry in memory for you. And this instruction returns an address. That's what it's supposed to return, and you can save that address into a temporary variable. So instead of creating a new temporary variable that corresponds to a register for each of our variables, we're going to create a stack entry for our variable and save its address. So now T1 contains the address of X, not the value of X itself. So when we go to use this variable, either to get its value, like in print X, we use the load. So the load will load a value of type I32. So you say load and the type of the value that you want to recover, and then give it a pointer to the address that you want to load from. So this is I32 star, means a pointer, and our temporary variable T1 holds the address of X, not the value of X, the address of X. So this will load whatever is in the address at T1 and store it into T2. So that's how we get our X for print X. And then we can call the print whatever we need to do to this temporary variable.
For
Yeah.
allocate.
For allocate.
Much like malloc, it's returning an address. Have we put X into that address already?
No. Well,
Put X into that.
so when you, just like in C, if you declare a variable and you don't assign anything to it, but then you go to use it, it's undefined behavior according to the C specification, but it'll work. The compiler will allow, many compilers will allow you to compile that program. And when you run it, you're just going to get whatever garbage, it'll be garbage value, but it'll be whatever was in memory at that point. If the OS is like zero initializing data, then it'll be zero. If the stack has been used several times and there's old data in the stack, it'll give you some old value that was put in there by another function. So yeah, so this is really like old school C, where we're really breaking down the elements of the language into their pretty close correspondence in machine code, or in this case, LLVM-IR. So declaring a variable is sort of readily translated into just making a new stack entry. Reading a variable or using a variable in an expression Yeah, reading a variable directly corresponds to, yeah, maybe I should have said store first, but reading a variable directly corresponds to the load instruction. And as long as you've been keeping track of which LLVM register holds the address of your variable, then whenever you see a usage of X, you can load that value from memory. You can create an instruction that loads that value from memory and create an instruction that saves that value from memory. Yeah.
So when we're building this up, the things we should keep track of are the names of every variable that's been declared and its memory location.
Yep, that's exactly right. And the memory.
We're not necessarily going to need to keep track of what's actually in the variable.
Right, you don't have to keep track, and you won't know because you may read it in from input. So you can't know ahead of time necessarily what will be in the variables. You just may not know. So that's why we create these addresses. And so for LLVM, strictly speaking, you don't have to actually store an address because the alloca function, you can generate an alloca function and save it into an LLVM register. Your symbol table can just hold, for at least for this project, the symbol table can just have two fields, the variable name and the LLVM variable that holds its address. Yeah.
Is it valid LLVM just to store %x instead of %t1?
Yeah, it is.
Do that?
I think so. I mean, as long as it's functionally equivalent, I won't even notice. Greater to triple won't even notice. Yeah, can do that. Yeah.
And if we were to have something like, say, a y equals x, print x, both of those would have to have a load command before, load the address of x before we could actually do the actual allocate x to y and print x, right?
Wait, can you say again if you have load?
So if I do y equals x, that's going to be, I have to load from the address of x and then
Store it in y.
And then store it in y. And with print, it would be the same thing.
Yep.
Load x and then that.
Yep. So you can think of, so this ties in really nicely with the grammar. So a factor can be an identifier. And so when you go to implement your extension to the factor part of your grammar, this dovetails beautifully into your expression syntax. You just have to add another little extra check for an identifier. And when you see an identifier, you just generate this load command, put it in a temporary variable, and just pass it around your expression tree just like you did before, just as if it's another new value. And this assignment expression or the print expression doesn't really care whether there was a variable inside of the expression. Your expression code generator handle all that for you. So the print statement will be exactly the same and will work exactly as it did in project 1. And then for assignment, you don't have to care whether there's a variable in the expression or not. You just generate the code for the expression and you'll get a temporary variable. And that is what you use to store into your identifier. Yeah.
When we see the identifier again, are we maintaining the table that keeps track of the symbol and the address?
Yes, you're maintaining the table. So as your classmate pointed out, you could use LLVM to kind of do that. Well, but you still need to, you need to have undefined variable references or undefined variable errors.
Mm-hmm.
So in order to do that, you need some memory of the variable. So you could certainly, as long as you do functional equivalence and you do stack allocation, there shouldn't be any way to game this. I don't think. You'll still have to keep track of the symbols in order to generate errors about undeclared. Because what happens if you don't do that? Then your LLVM is gonna have an error, the LLVM program, because you're gonna be using a symbol that hasn't been defined yet, and that's gonna break. Your compiler's not gonna break though. Yeah.
What if we see a variable but it hasn't been declared?
Hasn't been declared, then you give this error. You give this error message. So example 3 is an example of this. So if you look at this example 3, this is the simple C program. You can see it declares X, doesn't declare Y, but it uses Y. And we are expecting this to have this error. This error should be seen.
Okay, so how do we implement
That's a really good question. How do you implement the table?
That's actually what I'm asking.
There are tons and tons of ways to do it.
Okay.
Trading off between performance of the table and ease, simplicity of writing. So for last semester, when I did when I gave like a skeleton for this, I just used a linked list.
Okay, yeah.
It has terrible search performance, but it's really easy to write.
You could make it double, but not that much.
You can use a hash table, but then you got to kind of manage your own. I mean, there might be some third-party hash
You have
functions.
to come up with, hash function.
Oh, yeah.
You got to have a hash function. You have to be able to resize it. It's a lot of work to implement a hash function. I'm happy if you just use a linked list.
Java, then we wouldn't have to-
Hey.
Well, writing in C is part of the challenge. You really just feel the bits, you know. You're really at the hardware level.
I'd actually prefer C, so.
All right, so that's allocation, and yeah, why don't we end it here? 4 minutes early. I think it was a good place to end. And so next time we'll talk a little bit more about the symbol table and kind of type checking, although this isn't true type checking, but we'll kind of talk about what that is. And then we'll move on to code generation. And yeah. All right, have a good weekend, everybody.